Hello everyone, it's Dr. Zach. So today we are going to connect those Riemann sums or rectangles to figure out area to a definite integral. Let's get started. From your lesson preview, you should have remembered that area is the shape of a triangle in this problem. So that's 1/2 multiplied by the length of the base multiplied by the height. Now that height has a length of 4, but because it went downward, you came up with a negative area. And this would be unit squared if we had any sort of units attached to the problem. Now, when we're using geometry to figure out area, we're basically thinking about shapes and our geometric forms that we worked with before. Now, if we want to go from 0 to 1, once again, we have the shape of a triangle. So area was going to be equal to 1/2 base multiplied by your height, which was 2, and that, of course, gave you 1 unit squared. Now, I want you to think about what the answer would be if I was finding the area going from -2 to 1. For your second problem, you are asked to use antiderivatives to calculate f of x. Capital F of x is going to be x squared plus c. Then you were asked to determine f of 0 minus f of -2. When you completed that problem, you should have come up with -4, which matches the area under the curve. Same thing, when you found f of 1 minus f of 0, you get a nice little 1. Put them together, f of 1 minus f of -2, and your answer was -3. So did you notice that the constants canceled when you did your subtraction? And perhaps you wonder how the antiderivative is connected to the geometry. All right, so let's go back to what we were working on earlier. Area is the sum of heights of rectangles multiplied by their width, and those were Riemann sums. Area becomes equivalent when you take the limit as n goes to infinity. The notation, limit as n goes to infinity, and that delta x all becomes this integral from a to b of dx. So delta x and dx are, once again, equivalent. So what we're noticing is if we take our endpoints and place them into your antiderivative, you end up with the area trapped between a and b. The sum of the area can be negative if it's under the axis, and some of it is positive if it's above the axis. For example 1, we're going to determine the area of this given graph. Notice the endpoints that we're looking for are between 0 and 4. So area, unless you want to do limit notation, I don't think we do, it's going to be the integral from the lower limit, 0, the upper limit, 4, and the function, which is 4x minus x squared. Put that in parentheses, and we're going to cut on the x-axis. So if you were to draw one rectangle to represent them all, this would be what it looks like. So we next want the antiderivative, which is going to be 2x squared minus x to the third over 3. And don't forget your plus c. Now we don't want to lose our endpoints. We're going to draw a new symbol here from 0 to 4, that's that straight line, to tell us what we're going to integrate from. Next, we're going to think about, okay, taking the antiderivative, substitute the 4 in, minus the antiderivative, substitute your 0 in. F of 4 is going to be 32 minus 64 over 3, and plus c, don't forget the c, minus f at 0, which will be 0 minus 0 plus c. So did you notice that the c's once again cancel out? So they will always cancel out because the area under the curve is not going to depend on the value of c. All right, so that actually helps us out in that we will not have to write c's when we do a definite integral. And remember, once again, the difference between a definite integral and just an antiderivative is the definite integrals have endpoints. All right, going back old school. We're looking for the area under a curve using our Riemann sums. So first, let's find our delta x. Delta x is your b minus a over n, or 2 over n. Next, we want to find c sub k. You get to pick, so we're going to do the easy one, 0 plus 2 over n times k. Then we want f of ck Do our substitution now, and that's going to give us 4 minus k squared times 4 over n squared. All right, once we have f of ck, think about the limit notation. We have the limit as n goes to infinity, the sum k equals 1 to n of the quantity 4 minus k squared times 4 over n squared, and that is going to be multiplied by delta x, which is 2n. All right, now multiply this all out, and we get the limit as n goes to infinity, 2 over n multiplied by the sum k equals 1 to n of 4 minus our 4 over n squared times the sum of k squared for n, k equals 1 to n. All right, and then we do our substitution. So notice with the integral ideas, the limit notation and our substitution work hand in hand. So we have n goes to infinity, 2 over n. Substitute, we know that we're going to get the constant 4n. Notice if we integrated 4, we would get 4x when we're working with dx plus, and then you have your 4 over n squared, and the sum, when you have the sum of k squared, is going to be n plus 1 times 2n plus 1 all over 6. Now I want you to look closely at this part. When we were thinking about the limit, we were keeping the component numbers that remained as we went to infinity. Notice this 2 over 6 is 1/3. You add 1 to your exponent and divide by the new exponent. So this is where that exponent is coming from. That extra 4 is coming from the b minus a ideas. Now as we take the limit, we're going to get 2 times our 4 minus our 4/3, and that is going to be equal to 16 over 3. All right, so the Riemann sums tell us how to integrate. Now, number 3, we have a little bit of a problem with number 3. Let's take a look at it. You're told to find the exact area using geometry. Now, if I try to make these circular piece into squares, we're going to have a problem. What I need you to do is recognize this formula is a half of a circle, and connect the concept that we are looking for area. First, let's write area equals our endpoints 0 to 1. So we're going to integrate from 0 to 1 of our function square root 1 minus x squared dx. Okay, so here we have it. But you don't know the antiderivative of a square root function. Notice the x squared is trapped in the square root, and don't you dare do bad algebra. So you're going to have to recognize that this is a half circle. What do you know about half circles? It's not even just a half a circle. Since we're going from 0 to 1, it is a quarter circle. So the formula is for a half a circle, semicircle, and we want a quarter of the area of a circle. So 1/4 of pi r squared, that's your formula for the area of a circle, when r equals 1. And that tells us that the area is pi over 4. Pretty cool, isn't it? Now, if I went from -1 to 1, I would want 1/2 of pi r squared. So keep an eye on your shapes, because geometry might be your best bet for integrating some of these problems. All right, so you know at this point that if we have a lesson on something new, we need to include some trig. So let's find the area from 0 to pi of our trig function sine of x. Just recall, 0 to pi brings us to look at the right-hand side of this graph. If we were to draw a rectangle for Riemann sums, there's one representation. So the function's height is sine of x, and the width is cutting on the x-axis dx. Using your antiderivatives gives us the antiderivative of sine is negative cosine. Don't forget that value, negative cosine x, from 0 to pi. So first we're going to substitute in pi. We get the negative cosine pi minus negative cosine 0. Do your evaluation. and you should come up with 1 plus 1 equals 2. One more time, this was f at pi minus f at 0. So the area between 0 and pi is going to be equal to 2. Okay, now example 5 uses concepts from example 4. We know that the integral from 0 to pi of sine of x is equal to 2. And we want to determine the following. Negative area. So if I go from negative pi, notice that's my smallest value, to the largest value, 0, the area under the curve is still going to be the same amount, 2, but because it's under the x-axis, it's negative 2. Now, when we look at odd functions, and sine is an odd function, cosine is an even function, if we take the area from negative pi over 2 over to pi over 2, half of your problem is under the x-axis and half of the curve is above the x-axis. So if you take a negative value and a positive value and you put them together, your answer should be 0 if they have the same area. So now if we switch upper and lower limits, we talked about that. This one's now going from pi to 0. Okay, so let's think about that for a minute. If I'm going from pi to 0, here's pi to 0. The x's are now being cut backwards. So that is backwards distance, which is kind of strange. You have a couple choices. You can take the area that you know the answer is from 0 to pi and write write 2 and then put a negative in front. Or you can switch it up and rewrite this as negative integral 0 to pi sine of x dx. So if your endpoints are written from largest to smallest, you may switch the endpoints as long as you change your sign and you come up with negative 2 again. Now, if we have the lower limit and the upper limits equal, because it's an odd function, your answer should be. So the purpose of this example is to show you, if you know just one part of your integral, you can change your endpoints and still be able to answer multiple questions. So let's look at these two special definite integrals. If you're integrating from a to a, that means that there's really no b value going from a to a, then the area is 0. If you are integrating from b to a, that's going to be equivalent to the opposite of a to b. We also know that we can add pieces of integrals. If I integrate from a to some value of c, and then integrate from c to some value of a, that's going to be the same answer if we go from a to b. And splitting up our integrals is sometimes very useful, especially for a problem such as number 6. So I'm going to be integrating this absolute value function. What we're going to do is split it. Now think about the natural places to split this function. I believe we should integrate from -1 to 1 and then from 1 to 2 because our shapes will be triangles. So when we do that, let's rewrite it. This is the integral from -1 to 1 of our function, absolute value of x minus 1 dx, plus the integral from 1 to 2 of the absolute value of x minus 1 dx. Now, just like that circle problem, find the area using geometry, because sometimes geometry is just easier. You will have, for the first triangle, 1/2 base times height, plus second triangle, 1/2 base times height. And then the total area under the curve from -1 to 2 would be 2 1/2 units squared. Usually you don't have to write the unit squared, but I want to emphasize that this is an area problem. Now, if I wanted to rewrite this integral as the sum of two integrals without the absolute value, you're going to have to go and use the definition of absolute value in order to do that. So the absolute value of x minus 1 is equal to a piecewise function. It's x minus 1 when your x minus 1 is greater than 0, and negative x minus 1 when x minus 1 is less than or equal to 0. It doesn't matter where you put that equal sign. This can, of course, be simplified to give us x minus 1 when x is greater than 1, and negative x plus 1 when x is less than or equal to 1. So now rewrite your antiderivative. So this is going to be equal to the integral from negative 1 to 1, and those values are all smaller than 1. We'll use negative x plus 1 dx, plus the integral from 1 to 2 of our quantity x minus 1 dx. Next, you've got to integrate both of these pieces of the problem and evaluate between their endpoints. So we have a very complex problem when we solve using our definition of the absolute value. It will come out to be 5 over 2 once you do all of your substitutions. Your choice. You can use geometry to solve this type of absolute value problem, or you could use an integral. However, understand that the geometry only works when you have a linear function inside that absolute value. Let's summarize some of these properties we've been working on. Just like your summation notation, constants can be pulled out of definite integrals. You can split definite integrals up into addition and subtraction problems to make things easier for yourself. Now, if f is integrable and non-negative, that means positive, then the answer set should always be bigger than 0. And if f of x is greater than g of x, when you integrate, that inequality will hold if you're using the same domain. Okay, so give the lesson practice about 30 minutes of trying. And the lesson follow-up is on page 273. You have a fabulous day.